Hey, welcome everybody. Today we're going to go ahead and have our final lesson on rational functions, and this is lesson number 25. We're going to talk a little bit more about graphing, look at some of the special cases, look at some tables, and then a couple of word problems to finish things off. So notice here, I've tried to condense the list down a little bit in terms of what I consider to be the key values, and we're going to go ahead and start and try number 1 here. Now, the first thing you're going to notice, of course, is the fact that you have two separate fractions. So before we can go ahead and graph this, we have to add those fractions together. The way that you would add rational functions together is the same way that you would add any fractions together, which is by finding a common denominator. If you're going to find a common denominator, the first thing you want to do is factor those denominators to see if there's any way to make them just a little bit simpler. So if you go ahead and factor the first one, you're going to get 2 times x minus 1. If you factor the second one, factors of 3 that add up to be negative 4, that's going to be x minus 1 and x minus 3. That makes things nicer for us because when you're trying to find common denominators of these complicated rational functions, anything that's a repeat factor, you only need one copy of that in your new common fraction, and then anything else that's missing. So as I go to put these two things together, I'm only going to need one copy of the x minus 1 because just one copy is enough to include both. Then I need everything else that's left, which means I also need a 2, and I also need an x minus 3. In order to now decide what happens to my numerator, you're going to multiply this x plus 2 by everything that wasn't originally in the denominator, which means you're going to have to multiply it by an x minus 3. So that's going to be x plus 2 times x minus 3. Then be careful, there's a minus sign, so you want to make sure that you don't lose that. The only thing that you need to multiply the numerator by is a 2, and then negative 2x minus 1. So again, all we're really doing so far is finding a common denominator. I'm going to go ahead and just look at my numerator, so I have to FOIL. So first, outers, inners, last. Make sure you distribute the negative 2, gives you a positive 4x, and then a positive 2. And again, that's just my numerator. If you then go ahead and combine like terms, looks like we're going to get an x squared to start. Then negative 3 plus 2 is negative 1 plus 4x is 3x, and then minus 4. Luckily for us, that does factor even more. So factors of negative 4 that add up to be positive 3, that's going to be x plus 4 and x minus 1. And then remember, that is still, of course, over the common denominator. So x plus 4 times x minus 1 over 2 times x minus 1 times x minus 3, that essentially is my factored form. So I'm just going to go ahead and draw an arrow there. Notice, of course, that you can reduce, so that's going to be important to know as well. If I do go ahead and cross out those x minus 1s, I'm going to get a reduced form of x plus 4 over 2 times x minus 3. So good to have both. Remember, they both kind of play a role in terms of going to find that important information. So a little bit of an algebra review here before we go ahead now and review all the graphing components. So now that we have our factored form, let's go ahead and start trying to calculate all these different values, which by this point we have done many, many times. To find the vertical asymptote, you are, of course, going to look for any non-common factors of the denominator. So you're going to set x minus 3 equal to 0, and that's going to give you a vertical asymptote of 3. Then for there to be wholes, you would have to have a common factor to the top and bottom, which you do, x minus 1. If you go ahead and solve, your whole is going to be at 1 comma something. To find out what the something is, you would have to go ahead and plug the 1 into the reduced form. So you're going to go ahead and find, what was this called? It's an f of x, okay? So f of 1 into the reduced form would be 1 plus 4 over 2 times 1 minus 3. That looks like 5 over negative 4, so that's going to be negative 5/4. Then in terms of the n behavior, you mostly have all factored versions here, so you have to find a way to look at the standard form. So if you were to look at the numerator, you would have a 1x. If you were to multiply out the denominator, you would get a 2x. Because of the fact that they're the same degree is how we know there's a horizontal asymptote. And then you would go ahead and find those coefficients, which would be 1/2. Your zeros would come by setting any non-canceling factor of the numerator, which would be x plus 4, which would give you a zero of negative 4. And we're going to go ahead and take all that information and start graphing it. So negative 4 comma 0, that is the 0. Then a vertical asymptote here at 3. A horizontal asymptote at 1/2. So obviously halfway between 0 and 1. Then your whole, so your whole is located at 1 negative 5/4. So that's 1 negative 1.25. And again, draw it as an open circle. Then from here, if you want to go ahead and find a couple of additional values, the y-intercept is usually a good one. So if you go ahead and plug a 0 in at any time along the way, you're going to go ahead and get a y-intercept of negative 2/3. It's going to be right here. And again, as far as how many additional points you have to have, I will tell you for sure on the assessment. But for now, if you want to just do a couple, if you were to plug in 2, you would get back negative 3. And that would be enough for you to find this branch of the graph. Of course, crossing at the x-axis at negative 4 and then following along the asymptote. Let's say you want to find something to the other side of the asymptote. If you were to plug in 4, you would actually get back 4. And again, that's enough for me to know that this branch of the graph looks like this. So notice that even though the problem started off looking quite complicated, it actually ended up with a graph just as similar as the ones that we've seen. And then once you have the graph, I think is the time for you to do the domain and range. So negative infinity, first you're going to break at the whole, which would be 1. Then you are going to go from 1 to the vertical asymptote, and then from the vertical asymptote to infinity. Then for the range, you're going to go from negative infinity up to negative 5/4. Then from negative 5/4 up to the horizontal asymptote, and then ultimately from the horizontal asymptote up to infinity. So again, even though you technically can find the domain without the graph, you certainly can't find the range. So in my opinion, I would go ahead and make sure that you make the whole graph first, and then go ahead and find the domain and range afterwards. So just double checking that I got all that in the right order. Yep, I believe so. So now let's go ahead and take a look at number 2 and 3. You'll notice that number 2 and 3 don't have a list, and I think you'll see why in just a minute. So let's say you were to come across something like number 2. You would look at it, and first of all, you would identify it as a rational function because of the fact that there are polynomials in the numerator and the denominator. But then, something kind of interesting happens. If you go ahead and factor the numerator, you're going to get x plus 2, x minus 2, all over x plus 2. Before you even start to go ahead and try to start making your list, if you notice that you can cancel out those x plus 2s, all you're going to be left with is x minus 2, technically over 1. What you have here is no longer a rational function. This is just a linear function with a whole, or with a removable discontinuity or a point discontinuity. So there are occasions where if you wind up with only a 1 or some other constant in the denominator, it might no longer be a rational function, which means you don't have to fill out that whole list. You can just graph it the same way you always would, but just don't forget about the discontinuity. I mean, think about what y equals x minus 2 would look like. It's a line with a y-intercept of negative 2 and a slope of 1. We're going to graph it that way, but we're, of course, going to start by finding the whole. To find the whole, you find it the same way we've been doing this whole time. You would take the canceled factor and set it equal to 0. That would give you the x value of the whole, which in this case would be negative 2. You would then plug that into the reduced form, and you would get a value of negative 2, negative 4. So if I'm going to go ahead and graph this function, here's my whole, negative 2, negative 4. How would you graph x minus 2? Well, start at negative 2, up 1, right 1, up 1, right 1, a bunch of times. Down 1, left 1. Notice that going down 1, left 1 goes right through the hole, which it should. And as you go ahead and connect the dots, again, all you have here is a linear function with a hole in it. And to reiterate, that will happen anytime that you cancel, and all you're left with in the denominator is some constant, usually 1. How does that affect the domain and range? Domain and range, well, for the domain, you only have to break at the x value of the whole, since there are no other values. Then for the range, you're going to break at the y value of the whole. And again, because it is no longer a rational function, you don't have any other asymptotes to worry about, and you're all good to go. So even though these usually wind up being the easiest type of problems, some people find them confusing because it's just unexpected. Let's go ahead and take a look at another one. So here in number 3, this is h of x. So again, you look at this, you see all these large exponents, and you think to yourself, okay, this is definitely a rational function. Well, let's go ahead and factor the numerator. So the negative that's there has to remain. And then how would you factor x to the 4th minus 5x squared plus 4? Well, instead of factoring it with x and x, you would factor it with x squared and x squared. Remember, that's called quadratic form. How would you get 2 factors of 4 that add up to be -5? That would be -1 and -4. What you notice here is that you can actually reduce the x squared minus 1s, which would leave you with negative x squared minus 4. Or you could distribute and get negative x squared plus 4. That might be a little bit easier because what you have here is no longer a rational function. It's a quadratic with actually not only a whole, but 2 wholes, because of the fact that if you factored what you canceled, there would have been 2 of them. So this is actually a quadratic with 2 wholes. You do, of course, have to find those wholes, but then in the end, you're going to graph it as a quadratic as opposed to graphing it as a rational function. So to find out where those wholes are, you would look at your 2 common factors. You would set each of them equal to 0. That would give you x values of -1 and 1. You would plug both of them back into either of these forms. So -1 squared is 1, make it negative is -1, plus 4 is 3, and it turns out it happens to both of them. So again, when we go to graph this, all we're going to do is graph the quadratic, but we're going to have 2 wholes in it. So my wholes are at +1, 3 and -1, 3. A quadratic, negative x squared plus 4, that has a y-intercept of 4. That's going to have x-intercepts of positive and -2. If I go ahead and connect them, again, it's not a rational function. It is simply a quadratic with 2 wholes in it. And again, you could find additional points as needed. Plug in 0, 1, 2, 3, as many as you want, but that's good enough. Domain and range. So when it comes to domain, negative infinity to the first x value of the whole, which looks like -1, then -1 to 1, and then ultimately 1 to infinity. And then for the range, be careful. So you're starting facing down, negative infinity, getting bigger and bigger and bigger. 3 is the y value of both of the wholes. Make that a little bit more 3-like. And then as you get bigger, you're actually not getting bigger infinitely. You're only getting bigger to 4. And since 4 is the stopping place, you can go ahead and put a bracket on that. So again, these are just some special cases. You're likely to see them from time to time. So if it were to happen that everything cancels out of the denominator other than a constant, please make sure you know that that's fine. It simply means that you have some simplified function that's no longer a rational function, which actually makes life easier. So that's it for the graphing for the moment. Let's go ahead now and look instead at a table. Again, these are the types of questions you might be more likely to see on an AP test, things where you're asked to explain and analyze as opposed to create from scratch. So notice here, what we have here is values for a rational function, g of x. They are telling you that the denominator absolutely has 2x squared minus 4x minus 6 as a factor. And then there's a bunch of different questions that they're going to ask us. I don't know if I'm going to need to or not, but I'm going to go ahead and factor that just in case. So I'm going to factor out a 2. That's going to give me x squared minus 2x minus 3. That's then going to factor further as 2. Oh, sorry. I wrote 6, but I meant 3. So x squared minus 2x minus 3. Factors of -3 that add up to be -2. That's x minus 3 and x plus 1. So again, they have told me without a doubt that that is my denominator. So I'm going to want to keep that in mind. So in the first thing that they ask me, they want to know what is the domain of the function. So in order to answer the question, what is the domain of the function, as you look at the x values from left to right, because remember, domain is always x's, you would know that there has to be a break anywhere that you have some kind of value that is not included, or in this case, undefined. So notice that from left to right, -1 is undefined and 3 is undefined. You obviously can't speak about every single number. You can only use what's in this table here as a reference point. But as far as we're concerned, we're going to assume that the only restricted values are the ones that are shown, which means that the domain would be -infinity to -1, -1 to 3, and then 3 to infinity. Then, does either factor in the denominator also exist in the numerator? Give a reason for your answer. So does either factor also exist in the numerator? So the first thing you want to remind yourself of is that what would occur if there was a common factor to the denominator and the numerator? That would be where a whole was. So you want to go back and you want to look at this table of values and you want to try to identify, is there anywhere that you think is a whole? Now, if you go back to what we were doing in the previous lesson, when we were talking about wholes, you were approaching from the left side and you were approaching from the right side, but both of those sides were approaching the same values. So if you look at the values that are in question, those are the only places where there could potentially be a whole, where there's some kind of undefined. So if you take a look at the two options, look at what's happening around the -1 and look at what's happening around the +3. In order for there to be a whole somewhere, the y values have to be going to the same spot. So I think if you were to identify -0.4999 and -0.51, hopefully you would understand that those actually are going to the same spot. So I think it is safe to say that we have identified a value that gives me a whole, and therefore we have identified some factors. So lots of different ways that we could write this, but I'm going to say there is a point discontinuity, or you could just say whole, at x equals -1, because, and again, that's the whole point, or not the point, but that's what they're looking for. So yes, you can identify that it's at -1, but why? It's because as x approaches -1 from the negative side, which to say the left side, you're going to go ahead and put a little negative there, and as x approaches -1 from the positive side, which means the right, then the entire function g of x is actually approaching -1/2. So x plus 1 must be a factor of the numerator and the denominator. Now, again, there are lots of different ways you could say that. This is just for instance. And again, there was a tiny bit of new notation there, so I just want to point that out there. So up until this point, we have used the words left and right. So a little bit of new notation here. If you were talking about approaching something from the left side, you are going to draw a little negative sign up in the superscript. If you are talking about approaching something from the right side, you're going to put a little positive up in the superscript. So we're going to see that notation coming up in the next couple of lessons. Again, if you had just said left and right, that would be fine as well. But I want you to kind of get used to that. So again, this is the left side, where this is the right side. So the next question, and let me just get a new color here. The next question, does either factor of the denominator not exist in the numerator? So if you go back to the original, or you look at the denominator that they had given me, so we already identified that the x plus 1 is where the common factor is. So now we're looking at the x minus 3, which means we're looking at x equals 3. Well, look at what's happening on the two sides of 3. You have one of the values going to a large negative number. You have the other value going to a large positive number. Well, as far as we're concerned, that is actually negative infinity and positive infinity. Again, you're not going to be able to, the closer you get to 3.000000001, you're going to keep getting bigger and bigger and bigger. For now, you just have to be able to, extrapolate the fact that those are essentially negative infinity and positive infinity. So does either factor of the denominator not exist in the numerator? So there is a vertical asymptote at x equals 3 because, and again, the because is important, as x goes to 3 from the negative side, g of x is going to negative infinity. And as x goes to 3 from the right side or from the positive side, then the function is going to positive infinity. The only way that that can happen, that one side can go all the way up and the other side can go all the way down, is if here at 3, remember, on the right side, you're getting bigger and bigger and bigger. On the left side, you're getting smaller. That doesn't look so great. On the other side, you're getting smaller and smaller and smaller. The only possible way that that can happen, that those two values can be shooting off in opposite directions, is if you have a vertical asymptote there. So again, we know there's a vertical asymptote because they're heading off in both directions. Let me just make sure I wrote that right. So there's a vertical asymptote at x equals 3 because as you approach from the left, you're going to negative infinity. As you approach from the right, you're positive infinity. So x minus 3 does not exist in the numerator. And again, I can't stress this enough. Not only are you trying to tell me where it's happening, but most importantly, you're trying to tell me what is the reason. So be sure to give a reason. Then, based on the end behavior, does it have a horizontal asymptote, and give a reason. So remember, end behavior means you're going to look at the ends. So taking a look at the ends here, you're going to be looking specifically at the y values. At the left hand of the table, I see 1.98. At the right end of the table, I see 2.020. I think it's pretty safe to say that those two values are heading to the same place, which would be 2. So how do you summarize that? Well, first, what's happening on the left side? Well, that's what happens as x goes to negative infinity. The entire function g of x is going to 2. And then what happens on the right side, where x is going to positive infinity? Again, the entire function g of x is still going to 2. So y equals 2 is the horizontal asymptote. Then, last but not least, what must the leading coefficient of the numerator of g of x be? So if you know that the denominator, if we look back here for a second, the denominator had a leading coefficient of 2. We don't actually know what is going to happen in the numerator, but we do know that there is some coefficient. So we know that there's an x squared, and then we know in the bottom that there's a 2x squared. So let's give some letter to represent the coefficient in front of the numerator. Let's call it a. So the ratio of a over 2 determines the horizontal asymptote. So a over 2 has to be equal to the horizontal asymptote is 2. And if you solve, that means that a must be equal to 4. And again, you could write that in a bunch of different ways, but that's a perfectly good one. So this is such a great question, not even just from like a open-ended approach, but just the idea of being able to take all the information that you've learned so far and kind of work at it and look at it in a new way. It's really, again, just such a great question. And I would just advise you to go back and look at this, a couple of times because this is important. And again, pay attention to that data and pay attention to the notation. The idea of what x are you approaching and are you approaching it from the left side or the right side? And then where is the y value approaching? So again, such an excellent question. You'll see a similar one tonight. Last but not least, we're going to talk about a couple of real world applications here. So in order to kind of start that off, I want you to remember section 1.10. And 1.10 was where we talked about direct variation, which is y equals k times x, and then inverse variation, which is y equals k over x. And it's that inverse variation especially that I want you to look at, because y equals k over x, that looks a little bit like a rational function, which is why it's appropriate to talk about it in this unit. So take a look here at number 5. A local banquet hall costs $300 to rent the space and $20 per person for the meal. Write an equation for the average cost per person as a function of the number of people that are attending the banquet. So you're going to make it y equals or f of x equals or whatever you want. And you're going to go ahead and start with the fact that you have to pay $300 no matter what to rent the hall. And then $20 per person would be 20x. That's a linear equation. Of course, the more people that you have coming to your banquet, the more expensive your total bill is going to be. The key part here is they are asking you for an average cost. Think about how you find an average. You add up all the values and divide by the total number. So in order to change this to an average cost function, I'm going to have to go ahead and divide by x. Anytime you're talking about an average cost, you're going to have to go ahead and divide by the total. And if you don't know the total, then you call that x. So then it asks you to sketch a graph, and you have to take into account common sense and domain restrictions. So here's the thing. If you were hosting a banquet and you were inviting people to your banquet, what kinds of values would not make sense for your domain, which is the number of people that are coming? Well, hopefully you would agree that you can't have half a person or 3/4 of a person. You can't have a negative person, and you can't actually even have 0 people because then that would be a pretty terrible party. And plus, you can't put 0 into the equation anyway because you can't have a 0 in the denominator. So there really is no way to say that other than to just say it in words. The domain in this case would be the positive integers. You can only have positive whole people attending your party. So in terms of what the graph is going to look like, you're only really going to have something in the first quadrant because it has to only make sense. I would go ahead and suggest that maybe you just go ahead and make a little table here. Well, what happens if you have just one person at your party, 5 people, 10 people, 20 people? You could keep going, but you just need a couple points to see what's happening. So if you're the only person, you're going to have to pay $300 to rent it out, $20 to eat, and unfortunately, you're going to have to pay the total bill. If you plug a 5 in for all the X's, then it's $80 a person. 10 would be $50 a person, and 20 would be $35 per person. So you can see that the average cost is going down the more people that you have attend. Well, what happens if you have 1,000 people versus 5,000 people versus 10,000 people? Is there eventually going to be a point where it's not going to matter and everybody's going to be paying the same amount? Well, yeah. Keep in mind, this is still a rational function. Look at the degree of the numerator and the denominator. At a certain point, you're going to approach the horizontal asymptote, which based on everything we've learned should exist at $20. So what they're saying is that at a certain point, no matter how many people come based on the capacity, you're going to have an average cost of $20. And again, technically there would be a vertical asymptote also at x equals 0, since you can't put a 0 in the denominator. So 1, 320, 580, all we really care about the fact is that it's getting smaller. And so all you're going to have is this piece of the graph right here. It looks like a rational function, but it's only part of it in the first quadrant because nothing else is going to exist. So we already saw that $20 is the least you could possibly pay to attend this banquet. What if we want to know how many people need to attend for the average cost to be $22? Well, so if you want the average cost to be $22, you're going to set your equation equal to 22. Then you're going to cross multiply, subtract 20x, And turns out that if you have 150 people at your party, it's only going to be $22 per person. And again, hopefully that makes sense. That $300 that you have to pay no matter what, the more people you have to split up that $300, the lower and lower the average cost is going to be. And eventually, even though you yourself have to pay $20 to eat, if you have so many people that you're all sharing the cost of that $300, eventually it becomes negligible and you're really just paying $20 a person. So let's finish up with one more. A business is studying the cost to remove a pollutant from the ground. Here is the function that represents it in thousands of dollars to remove X%, which is given as a decimal. So in a case like this, I wouldn't ask you to write the expression. I just want you to analyze it. So the first thing they want you to do is they want you to graph it, and they want you to describe the domain and the range. So a little bit different than the first one. When it comes to the domain, okay, the domain is talking about what percentage of the pollutant you can eliminate, keeping in mind that you are expressing it as a decimal. So if you have a company that does not care about the environment at all, they could potentially take away none of the pollutant. Then if you have a company that's very green, they might take away all of the pollutant, which would be 100%. But again, because they're telling you to make it a decimal, that would just be from 0 to 1. For this case, if you know the biggest value of the domain, you can just plug in those values to find the values of the range. So to find the range, you're going to plug a 0 in to the equation, and that's going to give you a 0 back. If you plug the largest value of the domain in, which is 1, you're going to get a 150 back. And again, that's in thousands, so it's 150,000. If you were to go ahead and think about what this graph would look like, well, in terms of the theory, you can still calculate the horizontal asymptote. They have the same degree, so that's going to be y equals 15 over -1, which means your horizontal asymptote would technically be here at -15. Because of the fact, though, that we have already agreed that you can't take out less than 0% of the pollutant, you also can't, it won't cost you anything less than $0. So again, in terms of what we're going to do, I would suggest just making a little table. If you're going to make a little table, and we can kind of solve both of these at once. Sorry, that's not a table, that's a graph. So they want to know how much does it cost to get away 20%. We can just have that be one of our values in the table. So let's assume that you're taking 10%. Let's say you're taking 20%. Let's take 40%, and let's take 60%. And again, you're just going to plug those values into this equation, and I'll just save you a step. So if you plug in 0.1, you get 1.5 thousand. If you plug in 0.2, you get 3.3 thousand, 8.5, 7,000, and 18,000. Again, all we really care about is the fact that it's going up, up, up. Where should the graph start? Well, the graph actually is going to start at 0, 0, because that's the smallest value of the domain and the smallest value of the range. And then based on our table, we can see that it's going to be getting bigger and bigger, kind of in an exponential way. And it turns out that that's how the graph is going to look, because if this was just theoretical, the graph would continue on down here. But because it's a word problem, that part of the graph does not exist. And that's as much as we can actually graph. So kind of an interesting application. Again, I don't know how many of these you would see on the assessment, if any, but it's just kind of nice to talk about. So you're going to go ahead and try homework number 25 tonight. It kind of reviews everything today and then just reviews everything we've done in general. So thanks very much for tuning in, guys, and we will catch you next time.